Let me tell you a story about our planet, about us. But first of all, let me ask you, what do we all as people have in common? Well, for starters, we all live in the same place, Earth. We all tend to live in communities, towns, cities. We need transportation to get from one place to another. We work, sell, buy, trade. And most basically, we all need water, food, and air.
What's there? No glass, stand by 4. That lights out, air's up, 806.
So let me tell you a story while we're up in the air.
Photo 6 taxi to base taken runway 11, line up with to complete declaration.
Line up runway 11. NASA 426, clear for takeoff. We are set. All right, and 161 for flights. 80 knots.
Our story begins here. Flying over the eastern Atlantic Ocean, just south of the equator and right off the coast of Africa.
So we're here with the NASA P3 aircraft. This is an aircraft that can carry a large amount of scientific instruments. It's essentially a flying laboratory where we put a wide range of measurements of clouds and of aerosol particles to study both the chemical properties of the smoke and how it interacts with sunlight right on the plane.
So for each flight, we start off with a science objective that we have, something specific that we're trying to investigate, and we look at the weather forecast and the forecast for where the smoke is supposed to be, and we come up with a flight pattern based on that science objective. And so we have that preset pattern that's fairly locked in. So in some ways the flight is locked in, but then we make decisions once we're out in the field based on what we see for clouds and smoke and all that.
It develops in flight, so as based on the information that we get from the ground or from the LiDAR and people's interests. So there's a lot of banter on the plane, and that's always quite fun.
Clouds, smoke, atmospheric measurements, scientific instruments, a flying laboratory. So what is this group of scientists studying here?
So we came to this, for us, very remote, exotic location to study these clouds that you see offshore, and in particular how they interact with smoke that comes off of continental Africa.
So it turns out that Africa, to our best understanding, produces something like 30 to 50% of all the biomass burning aerosol particles on the planet. These particles can be from wildfires, we're familiar with those in the United States, or from burning of forests and croplands.
Well, I think it's mostly because of agricultural fires, and I think this has been going on for hundreds of years. It's part of the culture, it's the way that the soil gets replenished.
And they do that ahead of the rains. They do that before the rains come. So they burn the crops, renew the soils, plant new seeds, and generate the next generation of crops.
These are small fires, but there's many of them that smoke collects and gets brought up into the atmosphere, and the prevailing winds blow to the west this time of year. So they are able to carry the smoke all the way over to Brazil.
Aerosols project is really trying to study that in this region because there is such a large source of these particles over the continent.
The smoke produced by this biomass burning produces a large amount of particles called aerosols, which play an important role on our climate.
So aerosols are very, very tiny particles you can't even see. For example, in this small volume, that's about the size of my thumb, there may well be thousands and thousands of these small particles.
But they're different from other particles in that they absorb sunlight.
So the Earth's temperature is a balance of these incoming sunlight and the outgoing infrared. And if you change any one of those, the sunlight coming in or the infrared going out, then you have the ability to change the Earth's temperature.
If the smoke particles are over just the open ocean, then they look white from space and they're reflecting light back to space. So they're acting to cool the climate. But when these smoke particles are above low clouds, then they absorb sunlight, they darken the scene, and they end up warming the climate.
And so the project we're studying is to understand not the greenhouse gases, which we have a good idea about, but also understanding the aerosol particles and what role they play in this Earth's energy balance, the balance of incoming light and outgoing infrared.
Aerosol particles can become a very powerful climate-forcing agent, but they not only alter Earth's energy balance, smoke particles can also affect cloud formation and precipitation patterns.
There's another way that aerosol particles from the smoke can affect clouds. They can actually go into the clouds as the air over the ocean moves down into the clouds. And that interaction is such that every single cloud drop we see has to form on one of these particles. And if we affect the number, if we change the number by the smoke of these particles in the clouds, it turns out that it's essentially having more mirrors in the cloud reflecting sunlight back to space. So we think that the smoke can actually increase the amount of light going back into space. But by how much, we do not know.
So there are very fundamental questions in how aerosol and clouds interact with each other that we are trying to answer with the data sets that we are getting here. And we also think that by answering those, we'll better understand our climate, but we can address how precipitation patterns, for example, are changing as the climate is warming.
And so this is what Aerosols is really aiming to look at, is how does the aerosol affect the heating of the atmosphere, the amount of light scattered back to space, and then how does it change the properties of the clouds below?
Here's the dry air coming in.
One of the key objectives of the Oracles campaign, and for that matter, of any science campaign, is gathering valuable data that can help us address the science question we want to answer and better predict our climate. But how do you plan a science campaign to begin with?
Straight flow out.
Yeah, that's great.
ESPO is NASA's Earth Science Project Office. We manage airborne science projects for NASA headquarters, largely multi-aircraft international field campaigns.
Scientists, crew, technicians, but also equipment, supplies, logistics, permits. A massive scientific research mission requires planning ahead and effective management.
Well, ESPO begins organizing the campaign a year to a year and a half before the first deployment. So there's a lot of effort by a number of people toward getting country permission, getting aircraft clearance, logistics, how are we going to ship equipment, how much equipment, the safety aspects associated with that, and then how to handle the people, how to get the people who aren't flying on the aircraft to that country, get them permission to enter, place to stay, all the safety precautions, and transportation.
ESPO, the Earth Science Project Office, is in charge of managing the mission.
During the deployment, we coordinate and assist the science team in planning and implementing the flights they want to accomplish. So that means we are setting up a conference room. That means we are setting up WebExes, making sure they can communicate, making sure the internet is constant and fast. Working with the airport and arrange support, GSE, marshaling, janitorial trash emptying from the airplane, stairs, whatever the aircraft needs from the airport, we make sure it happens.
They are the ones making sure scientists have everything they need to keep working every day.
Well, the scientists need to have everything they would need back here in the U.S. They need a place to work, a comfortable place to work, office equipment, printers, connectivity, internet. They need a room, they need a screen, they need lighting, they need a hospitable environment, they need electricity, which wasn't always constant in Sao Tome.
Anything you need to accomplish your objectives during the mission, they are the people to go to.
So ESPO manages the project from the early planning stages through integration, through deployment, through de-integration, and through the return of everybody and everything back to the U.S.
We're here at NASA's Wallops Flight Facility, home of a portion of NASA's overall airborne sciences program, including the NASA P3 used in support of NASA's airborne science research programs.
NASA has a wide range of airborne science platforms. Depending on the mission requirements and the aircraft performance capabilities, one or more of them are selected. For the Oracles campaign, the P3 Orion was the perfect match.
P3's awesome aircraft to fly, great performance, stays in the air a long time, comfortable to fly in, very, very capable airplane.
So the P3 has 4 engines, or 4 turboprop engines. The aircraft has a wingspan of about 99 feet and about 110 feet long and about 33 feet high. Range is about 3,800 nautical miles.
Once the aircraft is selected, scientists have a powerful tool to do their research, but completely empty. To transform it into a flying science laboratory, they need to outfit it with the best tools and state-of-the-art instrumentation.
We use these aircraft for many different missions, and they're reconfigurable. Our team here basically will engineer a solution for whatever the scientist's suite of instruments look like, and we will go figure out which airplane to use and how to modify the aircraft to carry the instrument suites we do. So we're working very much, very closely a long time before we actually deploy. And then as we get closer, the science teams will bring their instruments here. They'll go through the integration process of outfitting the airplane with their instruments, and we then go through check flights and readiness flights, and then our mission ops team will work all the logistics that requires to be deployed to remote locations around the globe.
And for this deployment, that remote location is the island of Sao Tome.
So flight days are pretty long days. We get up really early, about 4:30, so that we can have a little bit of food before we come to the plane.
We have breakfast at the same table. We eat the same breakfast. It's more of a ritual now. Like, it's bad luck if we don't do that.
We get to the plane about 2 hours early to kind of turn everything on, warm it up, make sure everything is working properly.
I need about 2 hours to warm up my instrument, preferably more, but due to flight crew hours, we take what we can get, which is about 2 hours.
We take off, and then we spend about 8 hours on the plane taking measurements.
I'm on the flight for 8 hours, and then we're here for like maybe 10 to 20 minutes after flight, just collecting data and wrapping things up.
We turn everything off, we make sure everything's closed up and covered, and we're sensitive to water, so if it's raining, it's a little bit more hectic.
They're around, 11 to 12 hour days.
And then it's generally kind of go back to the hotel, save your data, eat dinner, and go to sleep, because they're such long days.
Long days, but they're good. They're good. The people make it worthwhile.
And you have just heard, in a 1-minute summary, the typical workday for scientists during a field campaign deployment. In order to collect as much data as you can, you have to make the most of the time you have available. Let's take a closer look at the work airborne scientists do during that time and the coordination involved to achieve their goals.
So a typical flight will last between 8 and 9 hours. We plan the flight the day before, and then we carry out the flight in the day with an investigator on the plane called a flight scientist.
Typically, you have the project scientist or the PI sitting in the mission manager seat, somewhat quarterbacking the flight, meaning they're getting information from the folks in the back and in the science stations in the back, also integrating some communication with the folks back on. Back at the home station, if you will, or the deployment site.
So a flight scientist is a person that sits up at the front of the plane and you talk to the pilots who are obviously going to decide where the plane goes or put the plane where you need it, and the scientists in the back. So we've got all these instrument teams in the back making different measurements, and the flight scientist both talks to the pilots and tells them where we want to go and what maneuvers we want to do and what timing we want, and also talks to the instrument teams in the back to get information from them and see what they're seeing, learn what they're seeing on their instruments, and also let them know what the next set of maneuvers is going to be.
Sometimes happens in real time. You have a notional plan set for the day, points you go to, and then what may happen, there may be a change of plan as, okay, we would rather do this, or the science is better at this altitude. So you have a mix of being in the clouds, out of the clouds, doing the aerosol work and the cloud work as well. So the aerosol missions typically have in and out of clouds with varying in altitude, and it becomes somewhat of a challenge in order to fly the profiles that they want to fly. And it's very rewarding to go back and look at it, the data they have, and you say, okay, I remember us doing that, climbing here, and having this spiral that takes place here.
Although flights are planned in advance, sometimes changes have to be made in flight and in real time to collect better data and achieve the science objectives.
As soon as the wheels come up, the understanding you have to have as a pilot is it does go dynamic when things change, and sometimes we can plan on doing something and then we have to scrap it and do something else if things go bad, or meaning when things go bad, things aren't going exactly the way you would anticipated.
Their job is to sort of keep things safe and make sure that they're flying safely, but also to try and get us good science. And so they are great at we ask them we tell them what we want, and if it's not a safe thing to do or it's not something they're capable of doing, they'll let us know and suggest an alternative. But mostly we know what works and what doesn't work. So it's really just a matter of walking them through, like, here's the next set of things we want to do. And they let us know if we're going to run out of fuel or time.
Good communication and coordination between the science team and the flight crew is vital to a successful campaign.
It's a communication between the front of the plane, where the crew are, and the back of the plane, where the scientists are.
We all come here with different expertises and different backgrounds, and are specialists in different areas, and so we have learned how to communicate better amongst ourselves.
When all the elements are set and the perfect conditions for doing science are met, researchers can really begin to do their job. During oracles, a large array of instruments and science teams are working together to gather information on aerosol particles, clouds, and sun radiation.
The instrument I run is the high-resolution time-of-flight aerosol mass spectrometer, so we call it the AMS for short. And what it does is we get a full chemical composition of the aerosol that we're sampling. So we're able to see in real time what the aerosol is made of in the atmosphere.
So we measure the size of the particles that are coming through, the amount of light scattering. So that gives an indication of the chemistry and composition of the aerosols themselves.
I'm part of a cloud probe instrument team. We have 8 instruments that are mounted under the wings. They measure the liquid water within a cloud as well as the cloud droplet concentration. We also can measure the sizes of the cloud droplets and whether they are ice or liquid particles.
So we have an instrument called 4-star, and it's a sun photometer. It measures essentially we measure the sun while we're flying.
We have an instrument on top of the plane which measures the downwelling energy, and we have an instrument on the bottom of the plane that measures the upwelling reflected energy.
The remote sensing instruments on board the plane are a radar and a LiDAR. The high spectral resolution LiDAR emits laser beams of light from the aircraft, and because it has 3 separate wavelengths, it can tell us about the amount and sizes of the smoke particles in the plume. Each laser is able to detect the bottom of the smoke plume with confidence, so that we know if the smoke is touching the cloud layer or not. The Airborne Precipitation and Cloud Radar is designed to detect both clouds and precipitation. This is a very important measurement, as precipitation may be affected by the presence of smoke. Other instruments characterize the water vapor and gases, the ability of the smoke to absorb sunlight and nucleate cloud droplets, and the size of the cloud droplets. The many instruments cross-check each other and help scientists interpret measurements from their space-based satellites. While gathering valuable data for further analysis is the main goal of this science campaign, it is not its only function. These real-time in-flight measurements are also part of the process to adjust the flight pattern in order to optimize sampling locations to collect the best data. All of this in real time.
So all of our instruments are in situ, so we see real-time data, which is very exciting. We can just look on our computer screen and we can see the droplet concentration. We can see how many aerosols are mixing within the clouds.
And so while we're flying, we're able to see what the aerosol is made of. So we're able to see how much organics are present, nitrates, sulfates, ammonium. And so we're able to tell the flight scientists exactly what we're seeing, when we're seeing it, what altitudes we're seeing it at, if we see something interesting, if we want to go back to this layer and sample. So it's a really cool piece of equipment to have because we're able to do everything in real time and go flight by flight to see what kind of aerosol there is.
So we're getting information from the ground. Please, can we go there? Scientists, oh, I'm seeing such and such on my instrument, and the air crew saying, hold on, I need to talk on the air traffic control. So it's juggling all of those 3 things. It can be quite stressful, to be honest, but it's enjoyable at the same time, and it's a great team that we're working with here. I've got a lot of experience in doing this, and so it's been a wonderful experience to be able to do this experiment in Sao Tome.
One of the things I tell folks when they ask me about how it is to fly for NASA is you got people that are very, very smart, and we know that this is very important. People wait years and years and years to get on the back of the aircraft, and it's very rewarding to me to be a part of that process and provide them that not necessarily the final piece, but that data piece from an airborne science platform.
All the data collected during the Oracles campaign will help improve climate models.
So we feel that the data sets that we're gathering here will allow us to improve how the ability of smoke to absorb sunlight in models can be parameterized, and that is a milestone. So that is something that will remain from here on out in all the models. And that's just one example of a fundamental contribution that we feel our oracles will be able to make.
The contribution that Oracles brings to science adds to our knowledge and understanding of our planet, to better predict the consequences that our actions have on the environment, and to help us make better decisions in the future.
We are living in a world with a changing climate that is becoming more and more clear. I mean, scientists have known this for a long time, but I think the general public now is really appreciating all the changes in the world.
The atmosphere is the region in which we actually live on every day of our lives, and the quality of the air is very important that we breathe. So it's very important to do this research, and I would like to be able to hand to my children and my grandchildren the ability to live in an atmosphere that is clean and is hospitable to human life.
We all benefit from understanding our weather and climate better.
So back to the question I asked you at the beginning. What do we all have in common? Yes, we all live in the same planet. We all breathe the same air and depend on the delicate climate balance to grow crops and produce our food. What happens in one place can affect other parts of the world, or even the future, our future. Our planet is an interconnected system, and we, as a species, are part of it.